Hey guys, so in this video we're just going to kind of review some of the concepts we went over in the February 12th R Help session. And those concepts include autocorrelation as well as kind of giving you guys a brief primer over transformations. So let's go ahead and get started by talking about some of the theory surrounding autocorrelation as well as some of the R coding you're going to do in order to test for this phenomenon. So a really simple way to think about autocorrelation is pretty much you're looking for a relationship in the residuals of your data set. And all we really want is that when we run a linear regression, we don't want autocorrelation to be present. When there is autocorrelation present, what this implies is that the independence assumption has been violated for the residuals, as you can kind of use one error to predict where other errors are going to be. And a lot of the time when you look at a residual plot, when autocorrelation is present, the equal variance assumption will be violated as well. Because usually we'll see a discernible pattern within the residuals, and as we know, that is something that we can't have when testing for linear regression. The two types of autocorrelation that are going to be relevant to the content of this course are positive autocorrelation and negative autocorrelation. So positive autocorrelation means that errors are followed by errors of the same sign. So typically what we'll see is points either increasing in magnitude away from the linear fit line, usually either going above or below the line. And negative autocorrelation means that errors are followed by errors of the opposite sign. And usually that means that one error, you're going to get one point in the data that's going to be above the line and then another that's below the line. And I know this sounds a little bit tricky to kind of explain and wrap your head around, so I'm just going to show you some pictures real quick of what this would kind of look like in the real world. So over here we have an example of positive autocorrelation. And you can kind of see that from this point here up to this point, we see that the errors in the data set are becoming more and more positive. So as we kind of have one point here, we see that it is a certain distance away from the regression line. And as we kind of increase up to this point here, the space between the point and the line increases. And similar when we go from this point over here down to this section of the graph here, we see that the errors are slowly decreasing in value until it gets more and more negative. So in summary, that's kind of what positive autocorrelation is. You're going to have errors which follow each other of the same sign. So from here to here we have positive autocorrelation in the increasing direction, and then from here to this point here we have positive autocorrelation in the negative direction. Negative autocorrelation, on the other hand, looks a little bit like this. And what we see here is that we have a positive error as our first point goes above the line, and then we have a negative error over here as our second point is below the line. And we can kind of see that as we progress up the x-axis, we kind of bounce back between positive and negative errors. So just to kind of clarify, this is what negative autocorrelation looks like, because we're kind of reversing signs as we progress along the x. And typically those are the two types of autocorrelation we're going to see in this class. In order to kind of test for autocorrelation, we're going to use something called a Durbin-Watson statistic. A Durbin-Watson statistic is going to be a number between 0 and 4. And pretty much what you're going to do with this number is you're going to get a table that's going to probably be given to you either during an exam or during your homework, and you're going to compare this Durbin-Watson statistic to two critical values that you'll find from this table. And the way you read this table, I don't have a picture of it here right now, but in order to find your critical values, you're going to use the number of observations in your data set, so that would be n, and then you're going to use the number of independent variables in your data set, which will be k, and then you're going to kind of see where k and n intersect on the table. And then those two values that you find at that point of intersection are going to be the critical values that you'll use for the Durbin-Watson test. And once you have your two critical values and your Durbin-Watson test statistic, you're going to kind of read and interpret your Durbin-Watson test as follows. So for example, if your Durbin-Watson statistic falls between 0 and your low critical value, then we say that there is positive autocorrelation. If it falls between your low and your high critical values, then we say the test was inconclusive. And if it falls between your high and 2, then we say that there's no evidence of autocorrelation at all. And so this first half of the table, from the values of 0 to 2, are really relevant if your Durbin-Watson statistic is between 0 and 2. And when your Durbin-Watson statistic is between the numbers 0 and 2, we say that there is a greater risk of positive autocorrelation compared to negative autocorrelation. If your Durbin-Watson statistic falls between the numbers of 2 and 4, however, then we kind of use this side of the table here. So if it falls between 2 and 4 minus your high critical value, then we once again say that there is no evidence of autocorrelation. If it falls between 4 minus your high critical value and 4 minus your low critical value, then we say that the test is inconclusive. And if it falls between 4 minus the low critical value and the number 4, then we just reject the null hypothesis and say that there is negative autocorrelation present within your data set. So now we're just going to go over some of the R commands that we'll need in order to kind of test for autocorrelation. So for this example, we're going to use the motorcycles data set. But before we load that data set, I want to point out something very, very important. So autocorrelation is only relevant for time series data. This is very important because that technically means within this motorcycles data set, autocorrelation is not going to be present because it's not time series, as we're comparing different series of motorcycles within the same point in time. The only reason why we're using this motorcycles data set is because it provides a good example of what autocorrelation would look like if we were using time series data. So just remember that when we're gonna go through this example, that while it does look like autocorrelation is present, there is in fact no autocorrelation because it's not time series data. I know that can be a little bit confusing, and I apologize in advance if that causes a little bit of confusion on your part, but once again, we're just using the set because it provides a good example of what autocorrelation would look like in the real world. So, to kind of continue, what I'm going to do with the motorcycles dataset is I'm just going to rename the variables MSRP and wheelbase. So when I do that, I'm going to name them just wheelbase and MSRP for the sake of simplicity. When we plot MSRP versus wheelbase, what we kind of see in our in our little plot here is that we see the regression line kind of going in this fashion here. But as we progress along the wheelbase axis, we kind of see that the errors are getting a little bit more and more positive, right? So typically if this were time series data, we'd be a little bit concerned with this trend because we'd say, okay, maybe there's autocorrelation present as the errors are getting a little bit more positive as we progress along the x-axis. So in order to kind of test for autocorrelation, what we're going to do is run the Durbin-Watson test. So in order to run the Durbin-Watson test, what we're going to do is run the first command, and that's going to be, if you've never run a Durbin-Watson test before, all you're going to type in is install.packages, and then you're going to put parentheses and in quotes lm test. And repeat, you only run this first command if you've never run a Durbin-Watson test before, because R pretty much needs to go and install the packages needed to run a Durbin-Watson test, as it doesn't kind of come standard with R. So once you hit run, it's going to install the packages needed to run the LM test. And then you're going to do that your first time, and you'll see that it's going to kind of load some of the packages down here, and it'll kind of notify you when it's done loading. So in order to kind of start testing, or in order to start running the Durbin-Watson test, we're going to run the first command, library, and then in parentheses lm test. And that pretty much primes R, letting it know that we're going to be using this package lm test, which is where the Durbin-Watson test is archived within R. And then just to kind of review, I had made a model and I titled it Model 1. And it's pretty much a linear model comparing MSRP and wheelbase. So once you've run library parentheses LM test, you're going to type in DW test and then the name of your model within the parentheses. So in this case, it would be DW test model 1 because I referenced model 1 as the linear model between MSRP and wheelbase. And these are the two variables we're testing for autocorrelation. So once we run that, what we're going to see is we get a Durbin-Watson statistic of 1.0792. And then what you're going to do with this number is compare it with two critical values that you'll obtain from a Durbin-Watson table. And to just kind of recall, I don't have the Durbin-Watson table on me, but it'll always be given to you either through the format of your homework or on an exam if needed. And what we see with this data set is we have 93 observations, so that would be n, and then we have one independent variable within our data set, and that would be wheelbase. So when you read the table, you'll find the two critical values for where you have 93 observations and one independent variable. And you find that the two critical values that you get are 1.63 and 1.68. So 1.63 is going to be your low critical value in this case, and 1.68 is going to be the high critical value in this scenario. So what we do is we take our Durbin-Watson statistic and we compare that to our low and high critical values that we have over here. And we find that our Durbin-Watson statistic of 1.0792 is below our low critical value of 1.63. So if we see the table that we pulled up just a second ago, we see that it falls within this region here as 1.0792 is less than 1.63. And that indicates that we have positive autocorrelation within our data set. And our p-value will kind of determine this, or will kind of confirm this, because we find that it's 1.027 times 10 to the negative 6. And as we know in statistics, if it falls below a certain alpha, such as 0.01 or 0.05, we can kind of reject the null hypothesis. So in this case, we'd reject the null hypothesis and say that positive autocorrelation is present within our data set. If your p-value is kind of above the alpha value, then we'd either say that it's inconclusive or we would not reject the null hypothesis. And just to kind of review, your null hypothesis in this case is that there is no evidence of autocorrelation, and you'd reject that when we find a trend of autocorrelation within our data set. So in summary, that's just kind of a little overview of autocorrelation and just kind of the tests that we would run in R in order to kind of examine our data and see if autocorrelation is present. And I just want to remind you guys that we're only going to use the Durbin-Watson test when we have time series data, because autocorrelation is only going to be relevant with time series data. So while we do have what looks like autocorrelation in this data set, we wouldn't actually say there is autocorrelation because this is not time series data. Once again, we're looking at wheelbase and MSRP at one point in time, and we're just using this data set because it's a good example of what autocorrelation would look like if it were time series data. So a good example in the real world of where you would see autocorrelation is when we're looking at stock returns versus time. And that's time series data, obviously, because we're looking at a certain stat in different time periods. And we say that there is often autocorrelation in time series data or stock market returns because that information does tend to be cyclical. So if you look at a business cycle, we'll find that it follows a lot of seasonal trends. So for example, a stock return in April could, for like 2017, could technically be used to predict a stock return for 2018. And we'd say that, you know, if it were to a significant degree, that there would be autocorrelation because you'd be able to use that error from 2017 to kind of predict where the error would be in 2018. So in summary, that is what autocorrelation is, and that is kind of how we're going to test for autocorrelation through the Durbin-Watson test for this class. So now that we've talked a little bit about autocorrelation, I'm just going to kind of give you a brief primer to what transformations are. So as we recall, when we run a linear regression, one of the conditions obviously is linearity, and we pretty much want to get the data between our y and our x axis to be as linear as we can. So when we look at MSRP versus wheelbase, for example, we can kind of examine a slight exponential trend here, because as we go along the x, what we kind of see is that the residuals get larger and larger, and as a result it gives the appearance that maybe this isn't such a linear data set overall. So in order to kind of test for that, what we can do is just kind of examine a plot of the residuals. So when we do that, we can just type in plot and then the name of our model. And when we run that, we're going to kind of get a plot of the residuals versus the fitted values. And so what we see here is that our red line of fit doesn't fall along this dotted line here. And that kind of indicates that the linearity assumption is violated, because we want this red line to be as straight as possible on this dotted line. And we can also kind of say that the equal variance assumption is violated as well, because what we see is a kind of a large collection of residuals on this side of the graph. And if we remember, when we're testing for equal variance, we want to kind of see no pattern in the residuals at all and kind of see it randomly distributed without this graph. When we hit return to see the next plot, we're going to get a QQ plot, and we even see that the normality of the residuals, it could be a little bit better, right? Because if you recall, we want all of the dotted lines to fall on this dotted line, or I'm sorry, we want all of these dots to fall on this dotted line that kind of runs diagonal across this plot. And we see kind of the dots running off of the line, especially at the edges. So that kind of indicates that while we do have some degree of normality, it could be a little bit better. And we're not going to be really using these next two plots a whole lot. I guess maybe we'll use this in the future. This is a good way to test for leverage, and this just kind of shows you, the degree to which outliers kind of affect our graph. But that's a subject for another video and not something we're really going to pay attention to here. And to just kind of see how good of a fit our model is, we're just going to run summary and then model 1, and that'll kind of tell us how good the fit is. And what we see is we have an R-squared value of 0.6602. And while that's okay, with linear regression, we know that we can do a little bit better of that. Once again, the R-squared value tells you the how much of the variance is accounted for between your two models. And while 0.66 is good, that, it could probably be a little bit better. So in terms of how you go about deciding what transformation is the best, I mean, that's kind of going to be a judgment call on your part. I mean, there are a number of different transformations we could run, whether it's an exponential one, a logarithmic one, or kind of maybe taking the reciprocal of one of our variables. And a big degree of what you're going to be tested on in this class is, can you run a transformation? And also, given a list of transformations, how can you tell which one is the best? And the way you kind of go about doing that is you're going to run the transformation in R, each of the transformations that are given to you, and you're going to analyze to make sure that all of the assumptions are met and also the R-squared value of that transformation. And kind of depending on, which transformation accounts for the most variation through the R-squared value, and which one kind of satisfies all of the assumptions the best in terms of linearity, independence, normality, and equal variance, you can kind of use the transformation which kind of satisfies the most of the criteria and say, okay, this is the best transformation that we can run. So for the purposes of this session, there are a number of transformations that we can run, but I'm just going to show you one example of a transformation we can do and kind of how that compares to our original model. So in this case, what I'm going to do for Model 2 is I'm just going to plot the log of MSRP versus wheelbase. And there isn't really any criteria for why I'm using log. This is just a simple example of one that I'm doing because I noticed this slight exponential trend within the data. Because if we kind of plot wheelbase versus MSRP again, what we see is an exponential trend towards the end. And so log would be a good kind of way to maybe tone down some of those y values and just maybe get a better linear fit. So I'm going to set Model 2 in R as the linear model of log MSRP versus just regular wheelbase. I'm going to run that, and then I'm actually going to go ahead and just plot it just to kind of take a look at what that looks like. So log MSRP and wheelbase. And when I run that, yes, so when we do that, we can see that the values on our y-axis became significantly lower, and we're noticing a little bit more of a linear trend here. And by toning down that y value, we kind of got rid of that exponential trend and managed to kind of all fit it within a linear, more linear looking plot. And to kind of check for our assumptions here, what we're going to do is run plot Model 2. And what we do, or when we kind of examine the residual plot, we see that this red line is much, much better. It's not as wonky. It's a little bit more straight, and while it's not perfectly on that dotted line, we can see that it's still doing much, much better than the original Model 1, where the line was a little bit more off-center and a little bit more bendy. In this case, we would say that, you know what, the equal variance assumption is still not satisfied here. And, you know, if we had a little bit more time, I could maybe run a couple more transformations and see which one would maybe suit the equal variance assumption a little bit better. But in this case, we would say, you know what, the equal variance assumption is still a little bit violated because while it's better than the first model, we see still a relatively large aggregation of residuals towards the end of the plot here. And that's typically not good because once again, we're looking for a random distribution of the residuals across this plot. When we look at a QQ plot, we see that the normality is a little bit better. More of them are falling on this dotted line, but we still would say that, you know, it's not perfect because towards the tail end here, at the right side of the QQ plot, we still see a large number of residuals kind of coming off of this diagonal dotted line. And so we know that we can probably run another transformation in order to kind of get those dots to fall on that line a little bit better. And when we run a summary of Model 2, what we see is that our R² value is 0.7753. And we can see that that is much better than the first one of 0.66. It kind of accounts for more variation. And that is kind of what we're looking for when we run a transformation. You know, we're looking to see and make sure that more of the variation is accounted for within our linear model, and also more of the assumptions are kind of satisfied based on, you know, taking the transformation of one of our axes. So, you know, while this transformation certainly is not perfect, there is probably different transformations that could fit. In the interest of time, this is the only transformation I'm going to show you, but just to kind of recall, you know, we can do a wide variety of other transformations. You know, we can kind of take the square root, you know, we can do reciprocals, and we could even, you know, do exponential functions and log functions. And I think those are going to be kind of the big transformations that we're going to see in this class. So I'm just going to write that down for you so you kind of know. We also got exponentials, logs, and powers. And when running a transformation, you can run a transformation of either your y variable, either your x, or both your y and your x. And pretty much, once again, all we're looking for is making sure that we get the highest R² that we can. And also, we're trying to make sure that our line assumptions, right, linearity, independence, normality, and equal variance are the most satisfied. And typically we're not going to find, a lot of the times we may not find that a transformation, necessarily works with our data. And a lot of the time, especially with autocorrelation, a big thing about autocorrelation is that, transformations cannot fix autocorrelation. It just tends to be a kind of a curse of the data in of itself. But when we're running these regressions, we just try and make sure that as many of the conditions as possible are satisfied, and that we account for as much of the variation that we can. So I hope that we were able to kind of help you and kind of assist with the concepts of autocorrelation, and also kind of give you a good introduction to kind of how we're going to be using transformations in this course. I know it's a lot to take in, but remember, I mean, you have our professors and our TAs who are going to be in their office hours and running help sessions to make sure that you have a good grasp of this these concepts before your first exam. So feel free to stop by if you have any questions at all, and we'd be more than happy to clear up any confusions that you may have. Thank you so much for watching. We'll see you later this week.